So good afternoon everyone. So today our topic is on digital recognition. So we have trained our neural network to recognize the digits from 0 to 9. So whatever digits or images we pass, so we make sure that it's able to predict the correct number. So before going in that, let's have a quick overview like how our architects looks, as well as we'll be discussing about each separately, about each layer separately in future slides. But to get an overview, so we have an image. Let's say here it is 1,1,28,28. So what does this say? That this is first of all first image, and here one says that it's of grayscale image, so it's just black and white and it doesn't has red, green, blue, that stuff. And 28,28 is nothing but its pixel size, like it's 28 width and 28 height. After that, it's being passed to, so there are two types of neural layer here. One is CNN and the other one is ANN. For the first one, CNN, inside that we again have two convolutional layers. So convolutional layer 1, where again inside that we have like kernel, and when we have like perform a convolutional operation, which we'll be discussing further, we get like feature map, and then we do something like max pooling, and the process keeps on continuing until we reach convolutional layer 2. And as soon as we reach here, before going to the ANN, we again do a process called as flattening, so that our ANN is able to accept those data. And after that, we just pass to the first convolutional, first layer that we have, ANN layer, and then the FC2 is our final layer, which shows the values from 0 to 9 that we are predicting. So we can consider FC2 as our output layer. So to discuss this further, with the help of coding and every layer, I need to explain a bit of internal thing, how it's working. So for example, this is the convolutional operation that is happening. So this is the image, let's say this is 28 by 28. And the green box that you are observing, that is going right to left, is nothing but a kernel. And here the kernel that is being used, it's for a vertical. So what is this specific use of kernel? It is used to detect the edges. So here you can see it's being able to detect all the edges here. So to understand it much more betterly, let's take an example that we have an image which is just black and white. And if we draw a matrix of it, we will be having some values like, let's say 0, and the bottom everything is 1. So when we put this 3 by 3 kernel, which is for detecting an horizontal line, horizontal edges. So when we just put an operation, we get a final output of something like 0, 3, 3, 0. So this is nothing but, this will tell us that there is a edge line like this. So when we compare this to our layer, so somewhere we had 32 kernels. So that means we had 32 such kernels which will detect various types of edges in our images. Clear? And this is for matrix dimension finding out. We will discuss this again in future slide. Going to the next one. Okay, this
slow down, go back please.
Okay, sir. There is no time limit?
The time limit is given by myself. So
okay, I thought I have to complete it within this one.
Okay. It's a nice demonstration, but you're showing a kernel 3 by 3. And your image is 28. How do you manage the border effect on the convolutional way?
How do you manage the
border effect that you have on the convolution?
Yeah. So for that, if you want to make sure when your border values are being detected, you have to add a padding, which is nothing but a 0 by 0 everything at the border.
So you're putting zeros.
Yeah, you have to put
adding zeros.
Yeah, you have to add a 0.
Yeah. Okay, go ahead.
Okay. So the next major topic that we have to know is about max pooling. So here max pooling, if you see, generally by seeing itself, we get an idea that our image is being reduced. So this generally they are used for two major purposes: to save the computational cost and to reduce this translational effect that we have something. So how to understand this? For example, again, let's say we have a matrix of image, some simple data, just to understand. And if we say we have a stride of 2, 2, so this is nothing but it will. You can imagine of a box. So for example, 5, 4, 9, 6, the first 4 values. So it will try to take the maximum value. So what's the maximum value there? 9. So now as the stride is 2, so it will directly shift from 2 pixels, 2 values. So from 5, 4 is directly going to 7, 1 and 8, 7. So now from that, what's the maximum value that we have? That is 8. So similarly, when the process is repeated, we get from that thing, the entire huge matrix, to just 9, 8, 7, 8. So that's the same thing that they are trying to show here. Once this is done, okay, this is our coding that we have done. So again, this will be part like differentiated again few next slides, but to get an overview, we have a CNN class in which we have defined like first layer. It will take like one is the image that's going to take. It will like give out 32 outputs. After 32 outputs, like kernel size as we discussed is 3, and padding as we just now discussed is like 1. Apart from that, the same thing is happening in convolutional second layer. And then we have a pooling. So pooling operation is common for MAC like first layer and second layer, so it's just defined once. And then we have FC1 and FC2. Those are nothing but ANN layers that we have. And that's about the definition like of init. And for forward, it's like again, okay, this can be better explained in like when we see the next slides. Okay, now coming to the first part. So here, as we discussed already, we got to know about this. And this is the kernel as we discussed here. Like we have from 1 to 2 up to 32 kernels, which detects various types of edges. And here, like how I came to know is it vertical or is it horizontal? So it's that is like I have not defined it. It's always like randomly and with the help of like what we can say backtracking and all. It will figure out its own edges, what it has to be detected. So that's for 32, and for each we have a bias. And this, when we do convolutional operation between this and this, we get the feature map. And this 32 output, like okay, now we are discussing about the matrix dimension, how here 28 came. So this n is nothing but the first 28 that we have from p is padding, so 2p minus f is nothing but the kernel size, that is 3. Plus 1, stride is that we are moving 1 pixel by pixel. So if we just do that, and we still get the feature map value of 28. So that was of this. Then moving to the next layer. So from convolutional layer 1, as we applied the max pooling operation, so this resulted in completely reduction of the size by 2 because it was 2,2 or stride was 2,2. So that resulted into 32, 1, 14, 14 as the total max pool thing. And this 32 data has been passed to the convolutional layer of 2, which will take 32 inputs. And this one has 64 kernels. So here it will be detecting 64 edges. And each one has again its own biases. And this is again the feature map of this. So the same operation is being performed here. And once we reach this step, we can't pass the data from here to the MLP directly, because here if you see, if you have observed, our data is in form of 14,14 or like 28,28, so it's more like a matrix. So when we are passing to an ANN, we have to make it flattened. We have to pass it separately to each single neuron. So for that purpose, we are going to first perform the flatten here. So it's like 64 into 7 into 7. So that many values we have, and that everything is being passed to our 128 FC1. So again, this has again own bias, and this will be passing to the FC2, which has again 10 things. So the FC2 will be using the sigmoid softmax, that we have used. For all the other layers previously we had used ReLU. Then apart from that, okay, that's it. Okay, and before again proceeding further, there is a surprise for us. Like when we compared between STD and Adam, we got to know that for us STD worked way better. Maybe because